Our first speaker is Jim from IBM. So, Jim, I'll let you take it away.
Okay, I'm here today to talk to you about Summit and Sierra systems and our deployment of those systems, give you a background on what we did with these machines. So the first part of the talk, I'll give you a background about these machines and what their capabilities are and how we predicted our performance and show you some of the results. And then that sort of lead you into some of the features that are shown up on these machines and how that helped us to the performance levels that we got to. And then I want to sort of shift and talk a little bit about the future and what we're going to do after these machines, since these have been deployed and are in production right now. So one of the things as we started the program is looking at, what are these supercomputers and how do they sort of vary versus, regular data center? Why did we go off and do something different? Well, it's real, and I think you're all pretty familiar with this, but it's really the sort of the synchronous communication and computation that needs to go on. The people really want to get to the bare metal resources. There's really coordinated parallel work going on. There's lots of message passing between these parallel work regions and stuff, like through MPI and stuff. And there are huge amounts of data kept on a parallel file system. The other thing is that these jobs can work, a really long time, hours to days. You need a checkpointing system, how to go past the reliability window, since the reliability window is a little bit shorter than the runtime with some of these jobs, and then a high performance interconnect. But as we look forward in the future, we see that there's a lot of things sort of influencing back and forth between the traditional data center and what we did with one of these supercomputers. So I just sort of want to put that contrast up and why we went to some of the special things we did. These are the specs coming off the machines. I think you've seen a lot of these. I mean, basically, Summit is the #1 system in the world at 200 petaflops. And as some people said, well, that's a nice number and stuff. But it is really some of those other performance characteristics that I'll touch on. And there's lots of good features in these systems to give you this kind of performance. So one thing I'm sort of proud is, and this is just an IBM view of when we've been on the top of the list, but some of this gap has been taken over by the Chinese and stuff. So it's good to see a U.S. system and our technology back on top of the list and leading the way. As just one measure of the performance characteristics of the machine. So as we got into how we were doing the performance, we actually have some of the unique ways of predicting the performance, and we actually had to do these predictions when we were first putting in the RFP for these machines. So there's a response back. So that was about 4 years before the machines came out. We just knew we were getting into GPUs, and if you go back into this time period, basically, nobody was really using GPUs in these systems. I mean, there was some stuff going on at Oak Ridge and stuff, but actually, projecting out, looking through what are we going to really get out of a heterogeneous system was a very complex task. So one of the key things that we did is we looked at the fundamental limitations of the system, looked at the applications and matched them up and said, what theoretically can you get out of these systems? And let's project our performance out of that. Instead of just saying, hey, let's run some traces. They're usually backward looking. It's old compiler technology and stuff. See what we get on them. So we did this forward looking. Let's look at the fundamentals of the machine and use that to base our projections on. Now, there are a couple different types of benchmarks. So one is there's 4 scalable science. So this is basically saying, let's take the whole machine and let's run a really, really big job on it. And how well can we do doing that kind of work when you take over a quarter or a big chunk of the machine running on the system. And then there's another type of workloads called the throughput ones, and this is when you have many copies of the same program running simultaneously on the machine, and you're basically just looking at how much throughput can you get on the machine, running a whole bunch of jobs on a big chunk of nodes and how they perform. And then there's 2 variants of these workloads that we looked at. So basically, the first one is our baseline, and that's where you only can have compiler directives, and you can't change the code base. So you can go in there and inject, things through directives and stuff. And then the optimized, we can basically take our gloves off and do whatever we want to get the performance out of the machine. And these are just some of the predictions and the different benchmarks that were in the system. So here's the basic results that you can see on these machines. So you can see that the blue line, that's the optimized, and then the line next to it was our target. And then there was the baseline, the green, and the target next to us. And so you can see on the left side, we have the Summit scalable, the Summit throughput. We have the Sierra scalable and the Sierra throughput. And remember, the basic characteristic between the Summit and Sierra, obviously Summit's a bigger machine, but it's got 6 GPUs per node, where the Sierra machine had 4 GPUs per node, and you got a little bit more bandwidth per GPU with the Sierra machine, since it has less GPUs. So the interesting kind of thing is to look at the optimized, and at first, to be proud of our numbers and stuff, we were actually very close on our predictions. So obviously, you got to hit these things to be accepted without buying a lot more hardware for these machines. So we were very proud that we could hit those optimized numbers. Now, the other thing that was very interesting is the baseline numbers, and you can see that we're ranging from like 32 to 82% above where we predicted. So what really happened in the time frame is OpenMP and a lot of the work we were doing with the compilers and stuff, we actually found a lot more fruitful work to run on these heterogeneous machines. Because everybody think, oh, it's so hard, you got to read code everything to do this. But this is showing that you can get actually very good results just recompiling your code, using these features through OpenMP to get performance out of this. So this should give you an indication. Don't be too scared of these heterogeneous machines and these GPUs, because you can actually put compiler directives in here and get very good performance out of these machines. And that's what sort of the balance between these 2 points was for. Now, the other important thing is to look at what are the scaling aspects of the machine and how well does it do running these big jobs and stuff. So this one basically on the left here is looking at the weak scaling model. So this is basically saying, let me just look at these jobs. It should just sort of scale with the machine as long as your bandwidths and interconnect and stuff can keep up. And you can see through the lines that we had good scaling as we increased the number of nodes. So you can see the nodes increasing there, and then the performance dropping. The time to execution dropping as we went forward. So the top line is the CPUs. That's when we just use the CPUs, and the bottom line here is when you use the GPUs, and those are obviously running faster on the system. So you can see there's good weak scaling on the machine. Then we looked at strong scaling here, and you can see how also with the strong scaling, and this is sort of saying I got one fixed problem, and I want to throw more and more resources at that one problem, and I want to see it speed up. And you can see the execution time and stuff is also coming down well. So that was with NAMD. And then this one here is another one showing you the strong scaling and how well the system is responding. So we were very proud of both the results. We're hitting the performance we projected. You get really good performance coming off, compiler optimized type of routines, and you see very good scaling across these as you go to very, very large types of systems and deployments in them. So this is what is sort of made up of the features. So the main things when you look at the node are that we have our latest Power 9 processors in here. We have NVIDIA GPUs. We have a fair amount of DDR4, so we call this sort of our fat node. So it's got a lot of bandwidth. It's got a lot of processing power. You put this in a drawer. This is all water cooled in one of these systems. So I think these are around 56,000 kilowatts in a rack as we pile these in, about 18 of these in a rack. So one way I try to drive this and just give you an idea of what's really going on in the system is look at how well are we using the different memory parts of the system. So over here on the right I show HBM, and this has got, this is sort of the relative cost to gigabytes per DRAM. So you see DRAMs here pegged at 1. There's lots of different variations of where you think HBM is probably a little bit over 2 times more expensive per bit than DRAM. So you have to be careful, when you're buying a lot of capacity of this. And then on the left side here, I wanted to put the relative dollars per gigabyte. So this gives you an idea how expensive the bandwidth is in these different types of things. So, the capacity across the whole node is 96 gigabytes. And basically I want to show you, if you had a GPU fully consuming this, how many seconds or fraction of a second would it take to consume and just basically run through the whole HBM. So you can go through the 96 gigabytes in 0.027 seconds. And then writing it back, if you're going at about half the speed writing it back, it'll take twice as long going back. And then if you come out of it, like a CPU coming out of it, it'll take about 6 seconds to go through the 512 gigabytes of DRAM that we have in the node. You can see that the network fill time is 51 seconds, and then if you're going to flash, the next level of memory hierarchy up there, it's in the around thousands of seconds to fill and write this thing. So you have to be very careful when you balance the system and you're loading the different things on here. Now the other key characteristics that we put in the system, we spent a lot of time on the NVLink, and you ever hear about the high bandwidth we have between the CPU and GPU. And this is to really drive this time down so that when we're moving from the DRAM, where a lot of your data is kept, how do we stage that into the GPU and make sure we have very effective bandwidth in this area? So I just wanted to show these numbers to give you an idea of what's going on there. So one thing we looked at is running some a joint type of processing when you basically go forward in time, and then you look at reverse time migration and sort of fill the time back in, and looking at sort of what we call a two-level checkpoint, or I call it two-level data staging, is how you move the data forward and stuff. So the blue and red dots here are representing the amount of work and where this is kept in the memory subsystem. And we balance the system here to say, okay, how do we really flow data back and forth from the DRAM into the HBM and stuff as you go through forward in some of these calculations. And here's some of the numbers showing you. It's up here on the top is basically showing you the runtime just using just regular running the RTM. And you can see the speed up we got from the NVLink versus regular systems with PCI and stuff. So one thing, there was a great benefit having that high bandwidth between the DRAM and the HBM and getting the performance out of it. We wanted to make sure this was scaling right. So the second bar down here is the weak scaling. So you can see that the performance was holding as the number of ranks went up per thing. And then you can see the strong scaling model also was coming down nicely too. So you can see our approaches developing this high bandwidth between the two parts of the system really paid off, and you can see it in applications and such as we deploy these systems. So one thing is we looked at this, there are a lot of mixed capabilities as we use these. There are a lot of different industries we designed this machine for. There's lots of different type of capabilities. So on one side, we look at sort of the analytics capability. This is kind of what we want to run on the CPU, a lot of branchy type of code. And then you have the massively parallel type compute capabilities. And through our heterogeneous systems, we mix these two together. And these are some of the things that you basically run on this. So how do we look at this as we go forward? So our next steps are really to look at what we call intelligent discovery and mixing in the middle of this AI with the workflows that you're creating. So we see that in the crux of this thing, you need machine learning running with your simulation runs and all that. At the same time, you're doing your large-scale simulations, and you look at the data analytics going on. So basically what we're looking at is how do we drive the computation of these machines dynamically as you're running your programs and actually rebalancing the system as we move forward. So there are a couple key characteristics that we need to be able to do this, and this is partly what we're looking at in the future is how do you design a machine in the future that can infuse AI inside of your run times and how you're actually going to do your computation, which is a very complex problem as we look forward. So this is one example that we actually did with Lawrence Livermore, was mentioned earlier today, about some of the work that IBM is doing with them. And we're basically, with this Splash app, we're basically doing a membrane modeling and stuff, but we've actually infused in the middle of this computation the machine learning. And that's sort of a key part, is we're actually driving this workflow with the machine learning as a key part of the work in the beginning. So one of the things, if you look on this bottom right, is how do we handle the data motion and control the information in the system. So we're coming up with something we call a data broker. And basically the data broker is something between the storage system and your main memory that allows you to exchange data between your workflows and sort of coordinate it. So think of it as a distributed key value store with the properties that allows you to share data between your applications and create natural workflows. So this has been a key part that we're developing with Lawrence Livermore on how we get these workflows working with AI sort of being in the middle of things. So as we came up with the data-centric concepts many years ago, we've been looking at how we kind of approach the system. These are our basic principles and how we've lined them up. So we have to create this innovative platform, and there are two important aspects. One is how do we create composable systems? So we're looking at not just the fat node, but how do we create the different parts so we can get the flexibility to resource balance across the system, get resource managers that allow you to apply different workflows like I was talking about and get things out of them. And the other thing is we make composable systems. What we're doing is also moving our software stacks closer to what the cloud stack is. So most people think about HPC and the cloud as a deployment system. We look at it as a unification of the architecture, how to get the containers and other pieces of the software stack working together and allow us to get on the same software stack that if you were deploying in the cloud to allow you to have a unified way of approaching these systems. So there's a couple novel approaches that we're looking at as we move forward in time. So one thing that's important is we're really getting to the end of Moore's Law computing. Everybody said, oh, it's going to be the branch out of new acceleration models and stuff. But one thing we notice is, is now we've submitted our stuff into exascale and stuff. We now need to look beyond where this is going to go. So we see sort of the next stage, and this is what we predicted many years ago, that even accelerators will start rolling over on Moore's Law, and we have to look at what are the next structures beyond that we need to do. So one key aspect, and this goes back to regenerating old ideas and stuff, is really looking at going to a data-driven control flow. So if you look at how control flow is working in a machine now, it's very complex. The way we actually use this process, you saw some of those applications where the utilization of floating point is very low. If you go to some more data flow and more data structured types of managing your control, you can really get those efficiencies up. So we're looking at the next stage of getting efficiency up to data flow. The other thing that we need to do is unleash the untapped potential of bandwidth that's in our system. So these steps are basically showing you getting the GPUs close to the HBM, but we really need to get our compute closer to the memory because that's where the bandwidth is. So we're looking at novel techniques of embedding our computation very close to the memory elements and looking at new structures to do that. And then sort of the foundation to all this is information security. So we're looking at new techniques and sort of using state-of-the-art rebuilding information security from the data and then moving it out. Right now, if you look at our systems, they're sort of a patchwork of sort of responding to all the security threats. We want to basically start with your data, which is your most important element, develop state-of-the-art security, and start building up from there. So basically, we've delivered these high-performance systems to labs. We're well prepared with these structures for the exascale systems. And now we're starting to look at the new structures and what we need to do to go beyond exascale and the next steps going forward. So that's what I have. Thank you.